Hello. Okay, it's been a while, but I hope you got plenty of time to work on your 2-3 workbook. And today we'll go over the remaining questions that we didn't solve from last time. Okay, so this will be the last lesson on chapter 2-3. And let's take a look at where we left off. All right, so the first question we have up is 18. It says, for function f of x, we're given a quartic function, x to the power of 4 minus 6x squared minus 8x plus 13 and constant k. Let g of x be the absolute value of f of x minus k. Given that g of x is not differentiable only at x equals a, find the value of a plus k. Okay, so we have a interesting function defined here. We have the absolute value of f of x minus k. Okay, so what we need to focus on right now is, given this function, what's its shape like, right? What properties does it have? And the easiest way to find that out is by taking the derivative. So let's go ahead and do that first. F prime of x equals 4x cubed minus 12x squared. Oh, sorry, 12x, and then minus 8. Okay. And let's see how that works out. Yeah, so we can group everything out by 4. X cubed minus 3x minus 8. Minus 2, sorry. Like that. And you can see this is a cubic expression that we can factor it further. So let's see if this polynomial could factor further, and we can remember our handy-dandy synthetic division method. So we write all the coefficients in order, but remember, there's no x squared term. That means we should write a 0 coefficient in that place, minus 3 and then minus 2. I think one will not work out because the sum of the coefficients isn't 0, but something close to that might be, you might want to try negative 1. Let's see how that goes. Okay, so negative 1 works, right? So remember, you put the number down, you multiply it, you add it vertically, you multiply it and write the number down, you add it vertically, and you keep going on, and if you get a 0 remainder at the end, that means that you're successful. And this is x squared minus x minus 2, and I think that factors further down nicely. So it's x plus 1 times x minus 2. So we had x plus 1 by this, right? This number, right? This number is whatever makes the term go to 0. So we got x plus 1. We have another x plus 1 from the quadratic here, and then we have an x minus 2. Okay, so we now successfully figured out the derivative of the function. It's 4 times x plus 1 squared times x minus 2. Okay, so if we want to graph that, we can graph that right now, right? So we have x plus 1 and x minus 2. This is a double root at negative 1, and that negative 1, since negative 1 is smaller than 2, we can sort of draw the x-axis here. This is going to be negative 1, this is going to be 2. Okay, so now we have our derivative like that, and we can draw our quartic function based off on that. So this is f prime of x, and f of x is going to look like, remember that the sign of the derivative here, the derivative is all about the sign. We go from negative to 0 here, but it still becomes negative. And then we go from negative to positive at 2. So we have a decreasing function. It briefly goes to 0 at negative 1, but we keep decreasing after that. And then we go from decreasing to increasing at x equals 2. So we get a curve like that, right? And this is going to be x equals negative 1, and this is going to be x equals 2. So that's going to be our function of f of x. Okay, cool. Now we know what f of x looks like, we can focus more on what are we supposed to do with this g of x. Okay, so the g of x is basically, hey, take this function, f of x minus k, where k is a constant, and then flip the bottom side up, right? And then it says that g of x should not be differentiable only at x equals a. Okay, so if you don't know immediately what this will look like, the best way is to try, right? The best way is to try. And let's see, let's put a line down. I don't know, if we put k way up here, if this is k, right? F of x minus k will essentially, will have the x-axis right over at where the line is, right? Because everything is going to get shifted down by k. So what we're actually doing is, based on this line, x equals k, right? This is going to get shifted down, so this will be the essentially be the x-axis, and we're going to flip everything up. When we flip things up, I think a key concept last time was that when you flip things up, if the derivative isn't zero, the sign is going to get switched like that. But if the derivative is zero, then the sign, well, there's no talking about sign because the left hand and the right hand derivative after that flip up will all be zero, so it's still differentiable. Right now, if x equals k is right up over here, we'll have two places where the absolute value function, g of x, will not be differentiable because this will get flipped up and this will get flipped up as well. But it says that g of x should only be not differentiable at one single point. And that single point, you might have guessed, is going to be right over here because we know that the derivative is going to be zero here. So right here, if we flip it up like that, it's still going to have a derivative of zero because the left hand and right hand limits match. Okay? And at this point is where it's not going to be differentiable. If we keep sliding the line down, it's going to be the same thing, right? There will be 2 points where it's not differentiable. And when we get to the final point, then if x equals k is like right over here, then is going to be 0 points where it's not differentiable. So the only possible option, so these all don't work, is going to be this line that goes right through this slightly, this momentary pause here. Okay, so if you recall the ratios of the quartic function, normally what you have to do is you have to set up this derivative, you have to get your x-axis in, you have to find all the roots by factoring, right? But since we learned those useful ratios for quartics, we can say that, hey, remember, it's 1 to 1 to 1 to 1. So it's 3 to 1 here, right? So the distance between this point and this point is going to be -1 to 2, so that's 3. So we go one space more, and this x coordinate will be 3. Okay, find a plus k. All right. So now we know that your a value is going to be 3 since it's not differentiable at that x value. And all we have to do now is find f of 3, and that will be k. So a equals 3, and k equals f of 3. If you plug that in, that's going to be, what, 81 minus 6954 minus 24 plus 13. So if you do 81 minus 54 minus 24 plus 13 should be, 78. Should be 16. 16 should be your value of k, yes. Okay, so k is 16 and a is 3, and your final answer should be a plus k, 19, okay? So it's all about figuring out what shape is my curve going to be, and figuring out that, hey, if I have an absolute value, I'm going to shift it down by that much and then flip it up. So it's essentially the same thing as flipping it up against this line and figuring out which of all of these possible cases is going to be the correct one, right? You're probably like, even, a lot of people think like you're going to like fall down to one answer immediately. The truth is, no, that's not the case. Every person has to go through trial and error to find the right thing that, to find the right case that fits for this problem. And the more you keep doing it, the more intuitive that process will get, okay? Cool. Number 19, the derivatives of the quartic function and the cubic function are shown below. Okay, so we have this graph given to us. Let's see if I can draw this. We have a cubic that has a local maximum at 1 and a local minimum at 3, okay. So it kind of goes like that. You have a local max and then a local min, sort of like that, right? And you have, let's draw this a little bit shallower. And then you have a derivative of a cubic function, so you should recognize that is quadratic, that has a local minimum at 1, and then it passes through the same point. The two curves intersect here at x equals 5. So we have something like that going on, and then since this is a parabola, it will be exactly symmetric like that. Okay, find the value of x where the function, so I should label which one's which. F prime is this one, and then g prime is that one, okay. And we're given a function hx equals fx minus g of x, okay. And we're trying to figure out where this is at a local maximum. Okay, as you recall, a local maximum, there needs to be a couple of things. The derivative must change from positive to negative, right? As we go from left to right, the derivative must change from positive to negative. Now, let's take the derivative of h of x. So h prime of x is going to be, remember we can take the derivative individually if they're adding or subtracting. So f prime of x minus g prime of x. And we need to investigate where that goes from positive to negative. Okay. All right, so if we go take a look at the coordinates where, oh, sorry, so this 2 should be at the point that they meet, like that, okay. We should look at the points where the derivative equals each other, right? Because at that specific point, the derivative is going to be 0, because these are all, smooth, continuous, differentiable functions, right? We need to look at where this function and this function intersect each other. So we have 3 possible points, right? We have this unmarked point on the left, we have x equals 2, and we have x equals 5. Now we need to show that this value should go from positive to negative, okay? So here, f of x is this curve on the bottom, so let's start from way over here. And g of x is going to be this curve on top. So f minus g, you're subtracting a bigger value from a smaller value. So this must be negative over here. In this region right here from x equals whatever that is to x equals 2, f of x is on the top, so f minus g must be positive. Here from x equals 2 to x equals 5, g of x is on the top and f of x is on the bottom, so f minus g must be negative. And beyond that, right, f of x will be on the top, so it's positive like that. So it goes from negative, positive, and we're only looking at where it goes from positive to negative, which is exactly at x equals 2, right? So your answer should be 2. Okay. Right, so this is again looking at the difference function sort of 2 functions. Okay, so let's move on to number 20. Okay. Number 20 says, for three polynomial functions, f of x, g of x, and h of x, select all that are true, and we're given three options. A says, if f prime of 0 equals 0, then f of 0 equals 0. Is that true? So if you're trying to prove something true, then you need to make sure it applies for every single possible case. If you're trying to prove something false, then all you need is one counterexample. So if you see something and you can think of a counterexample right away, then it's likely that the statement is false, right? And we can provide a very simple counterexample for this one, right? Let's talk about y equals x cubed plus 1. It could, the way to think about these is, can I craft a situation that violates this statement that I'm looking at, right? We all know that f of x, so f of x equals x cubed. X cubed looks like this, right? So it's tangent at 0, and then it goes up, but we're shifting it up by 1, so your function should look like this. So it is true that your f prime of 0 is still 0, but is f of 0 0? The f of 0 for this function is 1, so the statement cannot be true, right? So this was a pretty easy counterexample. B says, limit x equals x goes to a of g of x equals g of a for all real numbers a. This is true because this is the definition of continuity, and we know that all polynomial functions are continuous. So B is true. C, for all real numbers x, if h of x equals h of negative x, then h prime of x equals 0. Okay, so we're talking about polynomial functions. Let's take a look here. H of x equals h negative x should ring a bell. This means that it's an even function, right? An even function. And this even function must have a derivative of 0 if it's a polynomial. Okay. So let's see if this is true. So let's think of a few examples that we can do for this one. The easiest example that I can think of is the parabola y equals x squared, right? This is perfectly symmetrical about the y-axis. And you could also think of something like, I don't know, y equals x to the power 4. That's also, it's steeper, but it's also symmetrical, and the derivative is 0. So it kind of looks like there's no easy counterexample. Then we should try to prove it true for all possible functions. Okay, so an even function means that, remember, for polynomials, an even function means that there's a constant term. Let's call this a0. So that will be our constant term, plus your next term has to be x squared. Since, remember, adding an even function to an even function makes it even, right? So we have an x squared term, and then we might have an x to the power of 4 term. And we can have all these terms up to, let's say, x to the power of 2n, and then this will be your nth coefficient, like that. So this would be the template, sort of, the template for an even polynomial function. And let's take a look at when we take the derivative of this function. A0 is going to basically disappear. We'll have 2 times a 1 times x. plus 4 times a 2 times x to the cubed, and then plus blah, blah, blah. And then in the general term, we have 2n an times x to the 2n minus 1. Now let's try to compute f prime of 0. Well, okay, it says h prime. Okay, I'll stick with h prime then. So hx is even h prime x. As you can see, this is odd, right? Because it's only the sum of the odd degree terms, sorry. And there's no constant term, more importantly. Because when we plug in h prime of 0, all of these terms are going to disappear because they have at least one term of x in them. There's no constant term. Constant gets erased during the derivative, so we're guaranteed to have 0. So statement C is always true. Okay, so your answer for number 20 is B and C. All right, moving on to 21. Cubic function f of x has a leading coefficient of 1 and satisfies the following conditions. So our first condition is f of x has a local maximum value of 2 at x equals 0. Okay, so the very fact that we have a local maximum value and it's a positive leading coefficient, right, means that our shape is locked into this shape, right? Because all the other types of cubic functions, right, this one and then this one, they don't have local maximum or minimum values at all. Okay, so it has a maximum value of 2 at x equals 0. So let's just label that. There are 4 distinct real solutions to the equation absolute value. Okay, so we got another absolute value question. Absolute value of f of x equals 2. So now it's a matter of deciding where will our x-axis be. So when we flip it, there's exactly 4 solutions to this equation. Okay. All right, so now if you don't have any idea where to place the x-axis, then we should try and see if anything works or not, trial and error, right? So let's say we have to systematically do the trial and error, so we cover all the possible cases while not leaving anything out, right? That's the main principle for splitting stuff into cases and then trying to work them out. So let's start with all the way over here. What if the x-axis was all the way over at the top? Then our entire, this part of the function would get flipped like that. And remember that, oh, wait, we don't have to start here. We should carefully check the conditions and say, hey, if this is y equals 2. So, okay, I'm guaranteed to have my x-axis down here somewhere. Okay, that's good. If the x-axis was like way closer to here, then what would happen, right? If the x-axis was very close to the top here, then this bottom part will get flipped up. This part would also get flipped up. And this would be y equals 2. So we get 1, 2, 3, 4, and 5 solutions here. So that's 1 too many, right? So how could we bring that down to 4? If we placed the axis a little bit lower and then flipped it up just like that so that the local minimum would flip up to be the same value as your local maximum, I think that would be the golden case where we have 1, 2, 3, and 4 solutions. So let's draw that out. Okay, in order for the local minimum to have the exact same value as the local maximum when it's flipped up, remember that cubic functions are point symmetric, and this is the point of inflection. The line, the x-axis, must go directly through the point of inflection so that when we flip the bottom side up, our local minimum value becomes the exact same as our local maximum value, which is 2. So this part will also be flipped up, and then we can verify that the equation absolute value f of x equals 2 has 1, 2, 3, and 4, exactly 4 solutions. Okay, so this is our x-axis and this is our point of inflection. So this y-coordinate must be -2 since it's symmetric. And do we have anything else? Okay, so what we need to do is we need to find f of 3. So we need to figure out this function's equation. Okay. It has a leading coefficient of 1. So I think that might be a good place to start. Or, so our original function is this one right over here, right? So just keep in mind that this is the function that we're trying to find. Okay, what we could do is, since we know all of these points, right? At x equals 0, we have 2. So we sort of have, we can draw out the full coordinates right now. What we could do is I'm definitely curious about what this x coordinate might be. So we can set that up as a variable. Okay. Or we could, since we have the perfect 1 to square root of 3 ratio, we could also try doing that. But I think let's go with setting up a variable here. Okay. Now pay attention here. Here, our local minimum is at x equals t, and our local maximum is at 0. So we can find our f prime of x. Since the leading coefficient is 1, we know that the leading coefficient of the derivative is going to be 3. So it's going to be 3 times 0 times x minus t. So that's going to be 3x squared minus 3tx, okay? Now, what about our original function, right? Our original function. Now think about this. We know our equation for the derivative, and we know that it starts with an x cubed term, right? If we take the derivative and we end up with this equation, what will the equation for the original function be? Our x coefficient is 3tx, right? But that must have come from an x squared term. The 2 went down and it subtracted by 1, so it's x. The 2 went down, but it became -3, so -3t. So your original coefficient must have been -3 over 2t, so that when the 2 goes down, it multiplies with this, and it becomes -3x, or -3tx, right? And then the final thing to keep in consideration is the derivative. When we took the derivative right here, the constant term disappeared, right? So technically, there could be any constant that's in the function equation. We don't know just yet, but we do, right? Since our y-intercept is 2. Our y-intercept is 2. So when we plug in x equals 0, the function must have a y-intercept of 2, like that. So what we got here is we took the derivative and we managed to find the original function that it was from. Now, this is actually a preview of the next unit. The next unit is integration, where we walk through this process backwards, and we'll get. I'll explain more about this process in those chapters. But I think you can clearly understand how we got from here to here, because we already had this to begin with, and all we needed to do is figure out the coefficient for the x squared term in order for our x term to be like that. And then our constant here can be easily found from the y-intercept of our graph. So now that we got our f of x, all we need to do is to plug in t, right? So f of t, we know that it must be -2. So t cubed minus 3 over 2t cubed, right? Since this becomes t squared plus 2 equals -2. So we got, what have we got? Minus 1/2 t cubed. So why don't we move this to that side? So 1/2 t cubed equals 4, right? Since we moved the -2 to this side. So we multiply by 2 and we cube root it. So t must be 2. And that makes perfect sense in our picture as well. T must be a positive number, and we got t equals 2. All right, so our final thing to find is f of 3. So we can plug 3 back into our equation here. We got 27, t equals 2, so that goes back, and then we go 3 times 3 times 3, so that's actually -27, okay, plus 2, so these two cancel out, and our final answer would be 2, okay? So it's all about, right, figuring out the shape of the curve. We did that first, figured out what it means to have 4 different solutions to this absolute value equation. So absolute values is all about picking your reference x-axis and flipping it up and seeing how many points does it intersect, right? Okay. And then we set up the equation. So every time it's a little bit different based on the context here. Here, in this situation, this particular x-coordinate where the function is at a local minimum was important because we needed to set up the entire function, and we already knew that the maximum occurs at 0, 2, right? From the derivative, we figured out the original function. Again, this is, we'll get more into this in unit 3. And then we plugged in, found our value of t, found our function equation, and got our final answer. Okay, so it is a multi-step process, but I hope you got to practice at least getting deep into trying to solve this problem. Yeah. All right, so that was number 21, and let's go on to number 23. Okay, so 23, we have a composite function. So composite functions are really, if you take a full calculus course, it's going to be one of those like very tricky topics that might appear on the hardest problems, but you don't need to be intimidated by it. I think it's one of the most intimidating topics, but when you peel it back layer by layer and take it step by step, it's pretty manageable in the end to tackle. You just have to be careful with what you do. All right, so we have these functions given to us. F of x equals negative x cubed plus 3x squared plus 6. So we have a cubic function that's like decreasing overall, I guess. And g of x is a quadratic. X squared minus 2x minus 1. Let the maximum values, maximum and minimum values of the function f of g of x. Okay, so we need to identify our outer and inner function, right? So the outer function is f of x, and the inner function is g of x, right? So what we're doing here is we're starting from the inside and working our way out. We're going from x that goes into g of x, and that, remember, that inner function's range is going to be your outer function's domain. That's really the key of composite functions. So just keep that two-step process in mind. And yeah, okay, so I think the first thing to do is figure out what these graphs look like. So let's do that. F prime of x for the cubic function is going to be negative 3x squared plus 6x. And if we set that equal to 0, we can cross that out to negative x times x plus 2 equals 0. So x equals 0 or negative 2. Is that correct? negative, it's a plus. Okay, so sorry. So this is a minus, right? When we factor it out. So it's 0 or 2. All right, so it's a decreasing, well, it goes from positive infinity to negative infinity, I should say. Looks like this, and then we have our 0 here and our 2 here. So this is what f of x looks like. All right, so I think that's all we need to know at this point. We could find their values, but let's hang on for now. This quadratic function is going to be a parabola opening up, a concave up parabola. The axis is going to be negative b over 2a, negative 2 over 2, so that's going to be negative, that's going to be positive 1. So that's our axis right over here. Okay, so we're looking for the maximum and minimum values on negative 1, 1. So we have a closed interval of negative 1 to 1. So we start with our inner function, which is g of x, and we can indicate on our graph where we're looking for. So 1 is going to be over here, and negative 1 is going to be far up the parabola like that. And what we need to do is, since we're going from x to g of x to f of x, we need to find the domain range, the range of our function with our domain restriction, since our new range is going to be the new input of f of x. So g of 1 is going to be equal to negative 2, and g of negative 1 is going to be equal to 2, right? Yeah. Just plug them in, right? So our new input for f of x will be from negative 2 to 2. So we're not looking at negative 1 to 1 anymore, since that was x. We're now looking at g of x. The domain for our new input for f is going to be negative 2 to 2. So if we just look at our ratios here, we got a 1 to 1 to 1. So we got negative 1 right over here. So negative 2 is going to be way up here. All right, so negative 2 to 2. So this is the portion of the curve that we're actually going to be analyzing. So what is the absolute maximum for our function? It's way up over here, since we're guaranteed that negative 2 will be farther back than our negative 1. So your absolute maximum is at capital M. Capital M will be f of negative 2. And once we plug that in, it's going to be 8 plus 12 plus 6. Is that right? Negative 2. Negative 2 cubed is negative 8, so that's positive 8. Positive 8 plus 6 plus 12. So 14 plus 12, 26. It's going to be 26, and our absolute minimum value is going to be right over here. This is going to be our lowest point, right? F of 0. F of 0 is going to be 6. So therefore, find capital M plus lowercase m, it will be 32. Okay? So see, it's not that bad, right? It's not that bad after all. As long as we know how to apply the range of the inner function to the domain of the, that's going to be our domain of the outer function, and we can just analyze what goes on between our new domain. Okay, so the next problem is going to be 24. So I'm just going to erase this portion. Okay. The minimum value of function f of x equals 2x cubed minus 9x squared plus 12x plus a. On the closed interval 1, 3 is 3. So the minimum value is 3. What is the maximum value of f of x on this interval? Okay, so I think we got our derivative all sorted out here. 6x squared minus 18x plus 12 equals 0. We can divide everything by 6. We can do 1, 2, so x equals 1 or 2. So our cubic function has a positive leading coefficient, right? So we're going to have 1 here and 2 here. And I think you guys will be probably very comfortable with this process by now. But we were looking at 1, 3. Okay, so where's our 3? So if we look at our ratios again, see, this is very useful when we're comparing minimum and maximum, because we need to know if the 3 goes here or if the 3 goes here, right? So we go 1 to 1 to 1. So it's going to be 2 plus 1 half. 2 plus 1 half is 5 over 2, which means that 3 is going to be up here. 3 is going to be up here, and 1 is going to be right over here. So our maximum value of f of x is basically going to be this point. So plug in 3, 16, no, sorry, 54, right? 54 minus 9 times 9 times 9 times 9, right? Minus 81 plus 36. Oh, did we not figure out our a? Oh, we didn't. Okay. Let's figure out our a. How can we do this? Does it say the minimum value is 3? Okay, so I just missed that point. Okay, you shouldn't miss points like this. Okay, so let's plug in x equals 2 since this is our minimum point. So that's going to be 16 minus 4936 plus 24 plus a, and that has to be 3. Okay, so now we can get our a. 24 plus 16 is 40, and so a should be negative 1. And then we can just add negative 1 on our sum here. So 54 plus 36 is 90, minus 81 minus 1 should be 8. So 8 would be your answer for number 24. Cool. Number 25. Number 25 says the maximum and minimum values of cubic function. So we got ax cubed, so that means we don't know our coefficient yet. 3ax squared plus b on 1, 4, so closed interval 1, 4, are 22 and negative 18. So this is going to be our maximum value, this is going to be our minimum value, and find a plus b. Note, a is positive. Okay, so that's if you would call it a big hint, I guess, because a is our leading coefficient, and the fact that a is positive gives us at least a framework to work with. Let's see here. Let's take the derivative and see what we get, because we're not sure of a very specific curve shape yet. 3ax squared minus 6ax is going to be our derivative, equals 0, and fortunately, our a's cancel out, right? So we can cancel that out because we know that it's not 0. 3x squared minus 6x equals 0, so we can also cancel out the 2's. X equals 0 or 2. Okay, so that's a very big help for us. Now we know that. We have 2 different points where the derivative equals 0, so we got our shape locked in. This is going to be 0, and this is going to be 2. And basically, our minimum and maximum values for 1, 4, we can also figure that out now, right? So if we draw a horizontal line, it's going to be 1, 2, 1, 2, 1. So this is going to be 3, and 4 is going to be like way up here, right? So we're looking at 1 is going to be directly at the point of inflection, and 4 is going to be right over here above 3. So our absolute maximum, the curve that we're looking at is from here to here, is going to be f of 4. But let's hold on for that a little bit. What's our absolute minimum? Okay. Our max, okay, so we're not considering 0, so I guess we could go either way, but our absolute minimum is negative 18, so that's going to be f of 2. So 8a minus 12a plus b equals negative 4a plus b equals negative 18, so that's number 1. Number 2 is our absolute maximum should be 64a minus 48a plus b equals, what's 64 minus 48? 16a, right? 16a. 16a plus b must equal 22. And we can solve the system of equations. Why don't we multiply this one by 4, right? So 4, 1, 4, 4, 8, 32, 72, 72 negative 50, if we add them up, is going to be equal to 5b. So b equals negative 10. And a should equal, if we, what's a better place to put it? 40 plus b, right? 16a plus b equals 22. So b equals negative 10, 16a equals 32. So, yeah, okay. Yeah, so 32 equals 16a, so a must equal 2. And there we go, and we're trying to find a plus b. So a plus b is negative 8. All right, so these are all questions on local, not local, but absolute maximums and minimums. And as you can see, if you draw out the graph and just label where the numbers are, then it's not that big of a deal, right? You can physically visualize if 3 is above, like this line, and you can visualize the portion of the curve that you're trying to analyze. So this will be a big time saver. And you'll also be more confident in your answer because you can see that the graph is at the lowest point here and the highest point is here. Okay, so our next question is going to be 26. I think I hinted this question out last time. You can utilize geometry instead of setting up complicated algebraic equations. Okay, and this isn't necessary. I don't think this is a shortcut, but this is a necessary. Well, this is a pretty reasonable logical step to make when you're solving this problem. The problem says, what is the minimum possible distance from 3, 0 to a point on the graph y equals x squared? So we have 3 and we have x squared, sort of like that. And then I'm just trying to figure out what is my minimum possible distance. Maybe it's, I don't know, from here to here, I don't know. So this point moves along y equals x squared, and you're trying to find the minimum distance of that segment. All right. So what I hinted at last time is if I want to find the minimum distance between like this curve and a point, remember the set of all points that are equally distant from a single point is a circle, right? So let me draw a circle centered around this point, maybe something like this. And as I increase its radius, that circle is going to get bigger and bigger and bigger. Like that, and like that, until it eventually the circle touches one single point on the parabola. So when the circle is tangent to that curve, that's going to be our minimum radius, aka our minimum distance from these 2 points, right? So as long as we make the condition that the parabola and the circle are tangent to each other, and remember, when 2 curves are tangent to each other, it means that they share the same common tangent line, and we know that a property of the circle is the tangent line and the radius to that tangent point are perpendicular to each other. So we can apply that exact same logic to our problem here. So if we draw the tangent line from to this point, like that, sort of, then we must have our tangent line being perpendicular to our line segment here. Okay? All right, so if we call this point P and we call this point A, right? A is given. That means our slope of AP, so the segment AP, multiplied by slope of, let's call this line L, I don't know. So L is the tangent line, should be equal to -1 since they're perpendicular. And as you can see, this will very, very reduce the amount of algebra needed. Because if you were basically setting up the distance formula, you would have two squares, and then you would have all this optimized. But if we call this point P, what's a variable? I'll just call this a comma a squared, right? Because it's on the parabola. Then the slope of AP is going to be 3 minus a squared, right? So difference in x, difference in y, times the slope of L. Now the derivative of x squared is 2x, right? So the slope of L right here is just plugging an a into 2x, so that's 2a. That has to equal to -1. So we have the equation. 2a cubed. And then let's multiply 3 minus a onto both sides. That becomes -3 plus a. So we get the equation 2a cubed minus a minus 3 equals 0. And if you want to do some synthetic division here, 2, 0, -1, -3, we notice that the sum of all the coefficients is not 0. Okay, so what say 3 minus a? Wait, is this 3 minus a? Oh, sorry. If I was going to do a squared minus 0, then this should have been a minus 3. Okay, a minus 3, so that becomes 3 minus a over here, and this becomes plus, and then a minus here. Right, okay. So now we can actually try plugging in 1. So plugging in 1, because all the sum of the coefficients are 0, we're guaranteed to get a remainder of 0. And we do. So we got 2, 2, 3. So this is x. Can we factor this? I don't think we can. And the discriminant for this quadratic equation, we can use the even discriminant to 1 squared minus 6. It's going to be less than 0. So no solutions here. The only solution that we can get is x equals 1. So a equals 1. And our minimum distance then is going to be the distance between 3 comma 0 and 1 comma 1 squared. Okay, so that's going to be 3 minus 1 is 2, 0 minus 1, so that's 2 squared plus 1 squared. Square root of 5 would be your answer for this problem. Okay. All right, so that simplifies a lot, right? 27 is another sort of, we call these problems optimization problems, trying to find the maximum possible value or the minimum possible values under some constraint, right? Let's move on to 27, which is a optimization of area in when you're trying to, this optimization thing is a really famous example of calculus in real life, right? I think I talked about soda cans, right? You can set up an equation for the volume of a soda can, and then you can optimize that cubic function to find the ideal dimensions for a cylinder for a fixed volume. So if you want your soda can to be like 330 mils and you want to use the least amount of aluminum possible, then you can use calculus to find that optimal width to height ratio. And many commercial cans similarly follow that ratio as well. So that's a common application. For number 27, we have this situation. We have y equals negative x squared plus 12. So that's a parabola sort of sticking up like that. It's symmetric about the y-axis, right? And then we have a rectangle that's inscribed, sort of inscribed, not totally inscribed, but 2 of the vertices must lie on the x-axis and 2 of them must lie on the parabola. So we got A, B, C, and D here. And it says, what is the maximum possible area of this rectangle? Okay, so now you got to set up your variables like we set up our A variable here. I think a nice reference that we can make is we're going to let this length be t. And whenever you're setting up variables, it's very nice if you write down the constraint. T must be positive. You might get questions wrong if you forget that this whole picture wouldn't make sense if like some variables were negative or some variables were less than this particular number. So for like these real life optimization things, and for any problem really, when you set up a variable, you should always be mindful of its constraints. So if we got a t here, then the height of the rectangle would be negative t squared plus 12, right? That's just the function value. And since it's symmetric, this would also be t. And immediately we got our area formula, right? So our area formula is going to be 2 times t times negative t squared plus 12. Okay, so that turns out to be, sorry, let me clean that up. That turns out to be negative 2t cubed plus 24t. Okay, and now we're trying to optimize that but how long can t go? It can't stretch beyond the confinements of this parabola right here, right? So t has to be less than the roots of the parabola. So negative x squared plus 12 equals 0, x equals plus minus 2 square root of 3. So the maximum that t can stretch is 2 square root of 3, and now we exactly know where to look for in this cubic function. Okay, so let's take the derivative d dt, or if you're, I think I've shown you this notation before. There's f prime, but you can also write, hey, I'm going to differentiate this with the letter t, since this is a function of t. But anyway, that notation will get much more useful when you take your full calculus course and you have multiple variables. But for this one, let's just take the derivative. Negative 6t squared plus 24 equals 0. T squared equals 4, t equals plus minus 2. We have a negative leading coefficient, so it's going to look like this. This is going to be negative 2. This is going to be positive 2. We're only looking at stuff from 0 to 2 square root of 3. So we go 0 is exactly at the middle here, the point of inflection. And we can check our x-coordinate here using our ratios, right? So it's 2 to 1, 2 to 1. So that's 4, that's 2. That should be, this should be 4, right? Negative 2, 0, 2, 4. Okay, now we got that. Let's see here. So 2 square root of 3, square root of 3 is definitely less than 2. So our 2 square root of 3 should be right along here. And we want the maximum possible area. So we actually don't need to compare these two. We just need to know that we just need to recognize that that is going to be our maximum when t equals 2, right? All right, so when t equals 2, that's going to be our maximum possible area, and let's just plug that into our equation. That's going to be 4 times 12 minus 4 is 8, and so our maximum area is going to be 32. Okay, another optimization done and dusted. So for all of these, the strategy is to get everything in one variable because we need to analyze the function here, right? So if there's like multiple variables that are given to you, like h for height and r for radius, for example, then you want to get everything down into one variable, use the process of like elimination to find a single function. Okay, so our final question is 29. So we're almost done with this chapter. Okay, so 29. The cost to produce X kilograms of product P in 1 day, measured, it says in dollars, is modeled by the function f of x equals x cubed minus 60x squared plus 1200x plus 4500. Okay. If 1 kilogram of this product is sold at $1,200, how much of product P should be produced in 1 day to maximize profits? Now, you should remember that profits equals your total sales minus your total expenses, right? I think we did that a lot in like elementary school, middle school math, perhaps. So let's make a profit function. Why don't we call that P of X? Our profit function is going to be whatever we sell, right? So we're going to sell it at $1,200 per kilogram. So X is the number of kilograms. So our total sales is going to be 1200X minus whatever it takes to manufacture that many kilograms of the product. So in the end, it's still going to be a cubic function, but with a slightly modified it's minus f of x, so we should put a negative sign on everything. Minus 1200x plus 1200x goes away. So this is going to be our function. Okay, so now all we need to do is take the derivative of our profit function. So x equals, what do we have here? 0 or 40. Right, and we know that the coefficient is negative, so our function will look like this. We got 0 here, we got 40 here. What's our restriction on x? So we need to produce something. We can't produce negative kilograms of a product. So x definitely has to be above or equal to 0, technically. You could, not produce anything, but it has to be equal to or above 0. And as you can see, for this portion of the curve, we get our profits are going up until this point, and then our profits are going down. And x equals 40 would be the optimal kilograms, don't forget the units, of product to produce to maximize our P function. All right, and with that, we have completed chapter 2-3. So it was a lot of content, yeah. So we studied, at the very beginning, we defined what an increasing and a decreasing function was. We defined local maximum and minimum. We related the derivative to everything. We studied the shapes of cubic and quartic functions and how those shapes are related to their derivatives. We analyzed absolute value functions, when absolute value functions are differentiable, absolute value equations, absolute, like we talked about global, local, minimum and maximum. We talked about going through different cases and trying to deduce things by working systematically, dividing different scenarios, synthetic division to help with factoring, and yeah, just a whole lot of good stuff, including these optimization problems and how that might apply in real life as well. So until the next class, so the next chapter is going to be our final chapter in differentiation. So now most of the examples that we did were pretty theoretical. I think for chapter 2-4, the applications are going to get a little bit more realistic. It's still math, but we're going to be talking more about like equations. We talked a little bit about absolute value equations, but we're going to talk about inequalities as well. as well as like how do we relate speed, velocity, and position and all that. So that's going to be a very like physics-like application of calculus. And we're also going to be talking about 3D stuff like volume and surface area and how that all plays out with our tools of function analysis and derivatives. Okay, so great work for keeping up so far with this chapter. Yeah, it was a big one. And I'll see you guys in the next lesson with chapter 2-4. Okay, all right, goodbye.